Okay, hi everyone, welcome to lecture 13 of our CS 466. And today we're going to see how to use linear programming to obtain relaxation algorithms and approximate algorithms for certain hard problems. Okay, so all right, and today we're going to have three parts. And the first part is, okay, so why do we need to do like linear programming relaxations? And then we're going to see two problems. One of them is the vertex cover, and the second one is the set cover. Okay, and we're going to see how like linear programming can come even to the rescue of problems that are really hard. Okay, all right. So here's our main motivation, right? So many important optimization problems are NP hard to solve, right? But they're important, which means that we really want to solve them. So just because something's NP hard doesn't mean we're going to give up, or we should give up, right? But then, but we know that they're really hard, right? Or at least we believe that they're hard. So what do we do when we encounter an NP hard problem that we want to solve? Well, something's got to give, right? And usually we got to give a little bit. So what we do is, instead of finding the optimum solution, because sometimes NP hard problems are decision problems, right? So you can say, well, what are we talking about optimization here? Well, but usually you can transform decision problems into search problems. Like, for example, deciding whether there exists a perfect matching. Sometimes you want to find the minimum weight perfect matching, right? So those are types of problems that if you slightly modify the problem, you can transform any decision problem into a search problem, right? And NP hard problems are no different. So suppose that we have an optimization problem, which is NP hard. So what do we do when we see one? We want to find approximate solutions to those problems in polynomial time, right? And sometimes actually, we even want to do that for problems in P that we know how to solve in polynomial time. But in this case, what we do is we want much faster solutions, right? Like the problem is in P, but maybe, it takes a long time to run the code. And what we'd like is that maybe you can give up on the best solution and maybe get a solution that's like almost best, but not really the best, but we can find it much faster, right? So that's the idea. So, and here's the template for some of the problems that we're going to see, right? So we saw linear programming, right? Which was minimizing like C transpose times X subject to like AX less than or equal to B. And now an integer linear program is a linear program where we require the solution to be integral. Okay, and if you remember in linear program, so this is the integer linear program. If we only had linear programming, we would have something like this, right? Like an X in Rn. But the integer linear program, we have that X is greater or equal to 0. That's why it's like the natural numbers, right? Does that make sense? So these are the integer linear programs. And well, what is the difference between the two of them? Well, we can just do a graph here, right? So suppose that we had a graph and suppose that we had two constraints. Let me put the constraints in red. So these are the linear programming constraints, right? So those two here are AX less than or equal to B. And then what is our feasible region? Our feasible region is this region, right? So we have, let's say we have two variables here, right? This is variable x1, and this is, or let's say x1 and x2. And then, so these constraints here, they're pinpointing to us exactly like x greater or equal to 0. But this would be a linear program, right? The region in green is the feasible region of a linear program, but in the integer program, what we have is we need to count only the integral points, right? So we would be talking about the integral points here. And we just put all of them here. And then we can just, then we'll see what we mean. That well, I'm not doing a very perfect grid here, but you get the gist. Then here here, right? And if you complete the picture here, you can see that there's all these points that are integral, and somehow there may be some of the points which are integral, which are like on the constraints, and some of them which are not, right? But then if we say, okay, we're optimizing in which direction? So let's say that this is the direction they were optimizing. So this is like minus C transpose, right? So if we want to minimize, we want to go as far like up this arrow as possible, right? Because this arrow is like minus C transpose, correct? So if we were solving the linear program, our optimum solution would be here for the linear program, right? Like this is the LP optimum. But you can see that this point is not an integral point, right? So to solve the integer linear program, we would have to find, well, among all the points, which one is the optimum? And for the integer linear program, we will have this one here, right? In our case. Does that make sense? Is the closest to the vertex. Okay, like that's the pictorially what we're talking about. Does that make sense? Okay, so we have this integer linear program, and you say, well, okay, like how bad is it to just require the solutions to be integral? I mean, can it be that bad? And well, okay, so the first thing before we talk about the bad news, let's give the good news, right? So it turns out that integer linear programs, like they're very expressive, okay? So there's a huge advantage to use integer linear program as opposed to just linear programming to describe a problem, because they're very expressive to formulate optimization problems, okay? They capture many optimization problems you may think about. But the disadvantage is that they capture so many important, interesting problems that they capture even the NP hard ones. So in particular, integer linear program is an NP hard problem, right? And it is one of the famous like 21, NP hard problems, right? So integer linear program is very, very hard. Okay, but still, like thinking about problems in terms of integer linear program is good if we can solve them using linear programming, right? So, all right. So the idea is, okay, there's this integer linear programs. They capture lots of cool problems. The disadvantage is that they're NP hard, but we know how to solve something that's very close to integer linear program, right? So as we saw, we can find a solution which is very close to the optimum of the integer linear program. But the question is, can we get this partial credit in life, right? And that's what we're going to talk about, how to solve the LP and use that solution to find an integral which is good. May not be optimal, but it will be good, right? So here's an example of an integer linear program. Let's just see an example of a very important problem which can be captured by an integer linear program, right? This is the maximum independent set problem. So what is the problem? Well, we have that G is a graph, right, on vertex set V and edge set E, and an independent set is a set such that any two elements in this independent set do not have an edge, okay? So if we draw a graph, so let's draw an example here of an independent set. So if I have this graph, for example, okay, so what is the maximum independent set here? Well, the maximum independent set of this graph will be exactly those three vertices, because you can see that in this set, in the subset of V, none of them are connected by an edge. Does that make sense? And then if you take any four elements, they will be connected by an edge. Does that make sense? Okay, so this is the maximum independent set problem. And here, okay, here's an integer linear program relaxation for it, right? So what do we do? Well, okay, so what do we want the variables to encode? So we're going to maximize this x, like sum of xv, where v is each like an element of the vertex set. So what is xv encoding? So xv is going to be 1 if we pick v in S in our independent set and 0 otherwise, right? So that's what we're going to encode the variables. And that's why we have these constraints. So these are the integral constraints, right? That's just saying xv can only take value 0, 1, right? Now, if you look at this maximization, what are we maximizing? We're maximizing the size of our set. And what are these constraints? So these constraints here, they're exactly saying what? Well, for each edge of the graph, at most, like edge UV, right? At most one vertex in my set S. Does that make sense? Because that's the definition of an independent set. Yeah? So you can see that this integer linear program exactly describes the maximum independent set problem, right? But the independent set problem we know is one of, is an NP hard problem. So of course you can already see an example, right, on how an integer linear program is capturing the maximum independent set. Okay. All right. All right. Okay. So then on our quest here to get the efficient exact or approximate algorithms for the problems of interest, let's say maximum independent set, here's the following strategy that we're going to have. What we're going to do is take your combinatorial optimization problem that you want to solve and formulate it as an integer linear program, right? And then what we're going to do is we're going to derive the linear program. We're going to derive a linear program from the integral linear program by just ignoring the integral constraints. And this is what's called an LP relaxation, right? Because we're taking the integer linear program and we're saying, there are some constraints, we're just going to relax them. We're going to make them easier to be satisfied, okay? So, and in the maximum independent set, what would we do, right? So for example, in the maximum independent set, how would we do this? Well, what did we have? We have maximize sum of x v subject to xu plus xv less than or equal to 1. So this is so far so good, right? For all uv in my edge set E, this is v in the vertex set. And then what did we have before? We had the xu is in 0, 1, correct? So these are the integral constraints, right? So what do? Well, we remove them and we replace them by easier constraints. We replace them by x0 less than or equal to xu less than or equal to 1. Does that make sense? So now this resulting program is a linear program. LP relaxation. Right? Because these are easier to satisfy. Correct? Okay, so now we have the LP relaxation, right? But the thing is, if you notice, we're still minimizing the same objective function. We didn't change the objective function, but now we have a potentially larger set of solutions, right? And why is that? Because this set here, like 0 less than or equal than xu less than or equal to 1, contains the set of only integral solutions. Does that make sense? So our solution space is higher, is bigger. So we're still minimizing the same objective function, but now we have a potentially larger set of solutions. So in particular, since we're minimizing, well, I guess the maximum independent set we were maximizing, right? But we can also write here that we're minimizing just by saying like minimize minus sum of xv, right? Like so. Okay, so I'm just going to put minimizing just because we have the standard formulation, right? So, all right. So we're still minimizing the same objective function, but over a potentially larger set of solutions, which means that the optimum of the linear program is less than or equal than the optimum of the integer linear program, right? Just because the solution space is higher, right? So because solution space like of LP is larger, right? Or in other words, we're like minimizing over bigger set, like strictly bigger set. Well, bigger set, let's say. Yeah. So, okay. So now, what do we do? Well, we can just solve the linear program optimally using any efficient algorithm that let's just assume that we know, right? Like the ellipsoid or interior point methods or something. And now, after we do that, what do we do? Well, let's look at the solution that we got. If the solution to the linear program that we obtained, right, it has integral values, then it is also a solution to the integral linear program, and we're done. Because this must be, right? Like if a minimal solution is integral, then it must be a minimal solution to the integer linear program, right? But now, what happens if the solution has fractional values, right? Because remember, if our linear program is integral, we can, we will know that our solution will be rational, okay? We can just, so this is true. And then, we can talk more about that in office hours if you'd like. All right, so what happens if the solution has fractional values? Then we have to devise some rounding procedure that will transform fractional solutions into integral solutions. Does that make sense? So we'll have to do more. So we just solve the LP in a black box way, right? So say, okay, take a solution to the LP. If the solution has fractional values, then we have to do something extra to round the solution, the fractional values to integral values, that will transform fractional solutions to feasible integral solutions, right? So there's a big, we want feasible integral solutions. And moreover, what do we want? We want the optimum of the linear program. Well, we know that the optimum of the linear program will be less than or equal than the rounded solution because it's just a small, less than or equal than any feasible solution, right? So this is just by feasibility. And what we want is to prove that the rounded solution that we had is less than or equal than some C times the optimum of the integer linear program. And this will be our approximation factor. Does that make sense? So in the minimization setting, what we want is to say, okay, I get the optimum of my linear program. I do something to this optimum, to the solution that I get to get an integral solution, which is feasible. And once I do that, I know that my rounded, and all I need to say is that this procedure that I do will not kind of get me a really bad solution. It will get me a solution that is like close to the optimal solution to the integer linear program. Does that make sense? So in our picture, if we just go back a couple of slides, right? In this picture here that we drew for the linear program, what we're saying is that, okay, we're going to find the solution in blue, which is the solution to the LP. And what we want is we want our randomized procedure to return maybe this solution or maybe this solution. What we don't want is the rounding procedure to return to us maybe, this solution. That's really bad, right? The green solution in the bottom. We want either the red or the blue dot. Does that make sense? So, okay, so that would be our strategy. Okay. And now that we talked a lot about the high level strategy, let's see how to execute this strategy, right? So, all right. But before we do that, which we're going to do in the next section, I just need to tell you a little bit more about the LPs, right? So because not all LPs are created equal, right? But and because of that, it's important to understand the geometry of your feasible set and how nice the corner points are. And you're going to see that in the homework problem 1. Homework 4 is already online. So you're going to understand, you're going to study a little bit how nice the corner points of your linear programming are, because they're the candidates to the optimum solution, right? So not all LPs are created equal. Some of them, it turns out that the corner points of the LP, like if you think about it, like the picture that we drew, right? Like there is this linear program, and then we can talk about these corner points because they are the candidate solutions, right? Usually, right? Some of them can be nice and some of them can be really nasty, right? But there's also different ways of characterizing these corner points, Okay, and these different ways of characterizing the corner points, they're quite important, right? And they show up. So, okay, now, when solving the linear program, it's important for us to understand this geometry of feasible set, how nice the corner points are, and also there's different ways of characterizing them, right? So here's one way, right? So let's say that P is our polytope, right? Which is our feasible region, right? So this is the set of all non-negative x such that AX is equal to B, right? So this is our feasible set, like our feasible region, which is our polytope. And okay, and now, well, there's something that's called a vertex solution, right? A solution in the polytope is a vertex solution if, okay, there is no non-negative vector y such that both x plus y is in P and x minus y is in P. So what do I mean by that? So let's look at our polytope here. We just yeah, so we have like these are in our inequalities and the green region is our polytope, right? So a vertex solution, okay, let me just use this guy here, is a solution that, you know, there is no y different from 0 such that both x plus y and x minus y are in the polytope, like in the polytope meaning the green region here, right? So we have the green region. And notice that indeed, if I pick this guy and I pick any direction, even if I pick a direction inside of the polytope, like, you know, if I look here, this is x, right? And if I say, okay, this is x plus y is in the polytope, but x minus y is outside of the polytope, right? So you can see that this is a vertex solution because you can do this for any vector y. But now, for example, if I take this solution, so in particular, this is a vertex solution, as you would guess, right? Like as your intuition would guess, solution. Now, what about the orange one? Is the orange one a vertex solution? The answer is no, because now here, if I take this direction, y, right, like x plus y, this is in the polytope, and x minus y, all of them in the polytope, right? So these three directions are in the polytope. So this one here is not a vertex solution. Does that make sense? Okay, so you can see how the vertex solution really captures like kind of the corner points. And there's another way to characterize them, which is, you know, there's other types of, well, corners, right? Another definition you could give is the extreme point solution. So X is an extreme point solution if there exists U, a direction U in Rn, such that X is the unique optimum solution to the linear program with the constraint P and objective U transpose X. Okay, so for example, if we had our polytope again, like the same polytope that we described, oops, let me just characterize, but these are the equations. Now, how do we characterize, for example, this point here? We can see that this point is a corner point because is an extreme point, because if we look at this direction here, if we minimize in this direction, we put it very explicitly here, right? So this direction U. Now, if we minimize in this direction, well, note that the point X here in pink, right, is the unique optimum solution. Does that make sense? So these are extreme point solutions. And now, basic solutions are a bit more complicated, right? A bit more complex to describe, but they're quite useful, okay? And you're going to see how they come up in optimization in your problem 2 of your homework, okay? So, and how do we characterize basic solutions? Well, okay, so we have here our linear program, and we have the constraint AX equals to B, right? And here, let's say that in your solution, let's say that the support of X is, these are the coordinates such that Xi is positive, is strictly bigger than 0. Okay, so this is the support of x. So for example, if x is equal to 0, 1, 2, 0, the support of x here, the support of x is the set 1, 2, right? Or maybe let's say the coordinates here. Let me not put 1, 2, but let's put like 1.5 maybe. Then the support here are what? They're the coordinates, exactly the coordinates. Well, this is the coordinates 2 and 3, right? Like we have x1, x2, like x1, x2, x3, x4, right? So the support of x is exactly 2 and 3, which are the coordinates which are different from 0, like strictly bigger than 0. Now, if you look at the support of x, right, which is a set of non-zero coordinates of an optimum solution, of a solution, okay, of a solution. Now, we say that x, and this x is in the polytope, right? So x in the polytope just means that x, satisfies this, right? So this describes the polytope. Now, x is going to be a basic solution if and only if the columns of A indexed by the support of x are linearly independent. Okay, so, and here's the thing, it turns out, okay, that the first two types of solutions, right, like you can see that they're defining the corner points, right, and moreover, what it turns out, okay, which is really nice, and I'll leave it as a practice problem, is that all of these are equivalent. Okay, all of these definitions are equivalent, as in they define exactly the same set of points, which are the corner points of our polytope. Okay, and you can prove that as a practice problem. We can talk about it over office hours. Okay, so it's important to understand them, and you're going to see in homework, in the homework now, problems 1 and 2, how this comes into play. Okay, all right, so now that we know that we have to pay attention to the geometry of the problem, let's see some actual problems.